Have you ever wondered why energy security becomes such a massive issue during tensions in the Straits of Hormuz? Hi, we are Team AspenTech, and today we are going to show you something exciting from our Aspen Plus project, the production of dimethyl ether, turning the CO2 into e-fuel, especially for the post-combustion industry.
So right now, I'm going to explain all the process of how we utilize this carbon dioxide that obtained for the carbon capture system until producing dimethyl ether using Aspen Plus version 14 as our simulation tools. For carbon capture system, we are using post-combustion chemical absorption technology, which require chemical solvent monoethylenamine, which is the MEA, that will react with the carbon dioxide using the exothermic reversible reaction, then undergoes further separation process to obtain 99.8% purity of carbon dioxide. For methanol synthesis plantation, the technology we'll be using is this carbon dioxide hydrogenation, which will undergo an endothermic reversible reaction where carbon dioxide and hydrogen will react to produce methanol with the help of catalyst, copper, zinc, and aluminum oxide in the reactor. Then it will undergo into 3 stages of separation process to obtain 99.93% of methanol purity before entering DME plantation. To produce the DME, dimethyl ether, the methanol dehydration technology will be used. Methanol will undergo dehydration reaction to produce DME with the help of catalyst solid acidic alumina. For the simulation, we successfully obtained 99% purity of DME. So this is the simulation of our methanol synthesis process. As you can see, we obtain 99% of purity for our methanol before entering to DME plantation. So this is the DME plantation for our final product. As you can see, we successfully obtained 99% of purity for our dimethyl ether. Just for clarification, the reason why we are using different files for our plantation is because each of our plantation are using different thermodynamic calculation method.
Hi everyone, I will explain the existing challenge and their solutions. First of all, power plants continuously emit large amount of carbon dioxide, making them one of the largest contributors to global warming. At the same time, industries are under increasing pressure to meet sustainability targets under the Paris Agreement. Therefore, we need a commercially viable bridge between heavy industry and global decarbonization targets. But how can we reduce the emission without disrupting the energy supply? Second, we found that the conventional carbon capture introduced a major paradox. MEA-based system requires significant energy for solvent regeneration, which increases the operating cost and reduces overall efficiency. And without utilization, the captured carbon dioxide simply becomes a sunk cost rather than a solution. Therefore, it is credited to note that with capturing carbon alone is not enough to meet our targets. Moreover, carbon dioxide utilization introduced further challenge. Hydrogen is expensive and resource-intensive, making large-scale conversion difficult. Besides, the reaction involved are equilibrium limited, where water formation can reduce the conversion efficiency and deactivate the catalyst. On top of that, integrating multiple process units leads to energy losses, safety risks, and poor overall economics. To overcome this challenge, we shift the perspective. Instead of treating carbon dioxide as waste, we treat it as a high-value feedstock for fuel production, which is the dimethyl ether clean fuel with 99% impurity. We adopted an indirect carbon dioxide to DME pathway via methanol synthesis, which is a mature and scalable process. Compared to direct conversion, this route is more stable, uses proven industrial catalysts, and significantly reduces the technical risk. Not only that, the pinch analysis for heat integration addressed the high energy demand from carbon capture. By recovering and reusing processed heat energy, we reduce external energy requirements and improve overall efficiency. This directly solved the energy penalties issue for MEA capture. Lastly, we implemented a multi-layer protection system to manage operational complexity and safety risks. These include process design like hazard analysis, automated control system, and environmental protection unit to ensure the safe and reliable plant operation.
While the 2030 SDGs lay the foundation, true decarbonization takes time. Our Aspen Plus model scales a CCUS to DME pathway for 2060. By turning power plant flue gas into clean e-fuel, as future engineers, we are turning power plant flue gas into clean e-fuel, providing a long-term solution that supports the Paris Agreement targets. Thank you.